Hi guys, welcome to the first live stream of the channel. Today we're going to try to look at the Kaggle competition for advanced regression techniques, which is the housing prices competition. And we're going to try to get a decent score in the competition. So this would be a much more in-depth walkthrough than usual. So let's hop into it. I'm going to create a new notebook for this competition. And let's just look at the data before we do that, actually. We have quite a good number of columns, 81 columns, so a bunch of different features, and we're going to be trying to predict the house price for a given one of these houses. We also have a text file that contains a lot of descriptions of the features, and we'll use that when we're pre-processing. So let's go into code, a new notebook. And I also do want to look at the leaderboard before we get into this. So we're going to try to, I have submitted to this competition before, don't worry about that. We're trying to aim for a good score. So the good score can sort of be determined by what other people have gotten in the leaderboard. And if you take a look at this, you'll notice there's actually a fair deal of cheating going on towards the top of the leaderboard, especially this guy who has a 0, this is RMSE, I believe. Yeah, root mean squared. Oh, log error. But to have a 0 means this guy somehow knows the answers. So I think. Hi, Darsh, how's it going? But yeah, so he somehow knows the answers. I don't know how he got it. But these other people who have a really, really low score, I believe they're all using external data that was not provided for the competition. So we're going to be trying to aim for the best score we can get while using just the data provided. And you can notice, where is it? Yeah, so these scores all look good. There seems to be like a jump right here, you can see. And if you look at all the notebooks above the 275 place, tend to use external data. So if we look at one of these notebooks, you can see it's using multiple data sources, and they have some private data set where they're using more data than what's provided. So we're going to sort of ignore those and just focus on trying to get somewhere around maybe the 0.11 is a really good score, or 0.12 maybe, to try to get close to the top of the leaderboard. Alright, so let's hop into the notebook now. Alright. Oh, it's good to hear it. Thanks a lot. Alright, so let's go ahead and import NumPy and Pandas to start. And as usual, we're going to load in the data using Pandas.Read Csv. I'm going to load it in two different data frames here. And I'm going to call them train 0 and test 0 because I want to sort of progress through the pre-processing in steps. Normally in my past videos I've used one function for all the pre-processing, but that's not really going to work here because we want to sort of work through the data as we go. So both of these we're going to use pandas.read csv. And we'll grab the file path up here, paste that in here and here, and this will be the test set and the train set. Let's also get the sample submission. So we can take a look at all this. So train 0, test 0. I notice I can't see all the columns right away, so let's go up here and type pandas.setOption, max columns to none. I'm glad you like the videos. Thanks a lot. Alright, so let's take a look at the features. So we're gonna have to why don't we open a text file and sort of just like write down all the steps that we need for dealing with this, because there's quite a bit. If we want to approach the model from like we want to optimize it as best we can, we're gonna have to sort of plan this out a little. So first thing we'll do is clean the data, which will involve like filling missing values, just making sure every column is the right data type. Then maybe we'll do some feature engineering, but I might also save that for later. And feature transformations. So I'll cover feature transformations in a bit. We're also going to, at some point, do feature selection, although I bet we'll probably do that after the model's been trained. We're going to need some sort of encoding, scaling, and we might also check out target transformation, which means in a regression task, sometimes the target might require some transformation as well, in addition to the features. So we're going to take a look at the target in depth and try to figure that out if we'll need any target transformation. Aside from that, then we'll move into the more of like the optimization phase, which will be model selection. That'll be picking a model, and then hyperparameter optimization. And then, I guess, ensembling. So this is the key to succeeding in a competition. This is really what makes your model strong, and I'll cover that later when we get to it. So let's start off with cleaning. Okay. So let's also look at the sample submissions so we have an understanding of what the end result should look like. So we have these IDs, and these are the IDs for the test set. If we look at the beginning here, you can see all the IDs, and then the sale price is the prediction made for each ID. So at the end, we're going to submit a data frame that looks like this. All right, so let's look a little more at the train set. So train0.info, and so this isn't so great because I'd rather just look at the is-and-a matrix actually. Let's sum over the rows to get the total number of missing values in each column. Right away we can see I can't see all the rows, so I'm actually going to go up to the top and set the row max also. I don't want it too big. I'll make it something like, I could just do 81, maybe 90. Alright, now we can see them all. So we do have some number of missing values here. We're definitely going to have to process them. Now here's something to consider. We are actually given the train and test sets. And so when you're dealing with a competition, in general the test set should be thought of as something you're not looking at until all the pre-processing is done. But when doing a competition, the rules of practicality for production purposes sort of go out the window, and anything is fair game as long as you stay within the realm of the rules for the competition. So we are going to stick with the data we're given, but I think we can actually extract some more useful information out of the test set because it is given to us. Let's look at test 0, and actually the is-and-a matrix of this one. You can see this also has some missing values. Now, when we want to fill these missing values, let's say we were doing mean imputation, right? We were filling by the mean of the column. If we combine the test and train sets, we'd actually have more information to use when calculating the mean of the column, because there are valid data points in the test set as well. We don't know the targets associated with the test set, but for something like mean missing value imputation, having the test set available to us is very useful. So what I'm actually going to do is I'm going to combine the train and test sets. And this is just for the purposes of filling the missing values. And after we're done with pre-processing, we're going to split them apart again. So when we do this, we just have to make sure that we don't shuffle the data at any point, because then our train and test sets will get mixed up. But if we concatenate them on top of each other, we shouldn't have a problem. Alright, so we're just going to use pandas.concat to take train 0 and test 0 and put them together along axis 0, which is stacking on top of each other. Now if I do this now, it's going to give us an error. Actually, no error, but it's probably, yeah, you can see the sale price column has all these missing values here. So what I'm going to do is strip off the target column before we concatenate them. So let's call it target. That's just going to be train 0 sub sale price. Whoops. So if we look, that would only take the train set, and the test set target wouldn't even be added. On the other hand, I'd also like to strip off the IDs. I would like to point out that only the test IDs are actually useful to us because we need them for this sample submission thing when we make our submission. The train IDs are not so useful, so we can just drop those. So let's save the test IDs. That will be test0 sub ID. And then what we're going to do is drop them from each. So I'm going to make train 1. So you can think of train 0 and test 0 as the raw data, and then train 1 is the next step up from the raw data. So train 1 is going to be train 0 dot drop the ID column and the sale price column. We can drop it because we already saved it into target. Dropping from axis 1. And then test 1 is going to be test 0 dot drop ID. And we can drop it because we saved it up here. Then we're going to concatenate train 1 and test 1, and we're going to call this data 1. So now data is sort of like it's all of our data, right? Train and test. Let's take a look at data 1 when that finishes. So we don't have a test column, an ID column, and at the end we don't have the sale price column that's given by target. Alright, and this is pretty good because now when we're filling for missing values, we can look at more data for preprocessing. Alright, so for cleaning, let's focus on first. How should we say it? We want to set the data types correctly. Ensure proper data types. So if we look at data1 dot select dtypes, numpy.number, this will give us all the numeric columns. We can try to look in here for any features that have been encoded as numeric but actually should be categorical, because any such features we want to set them to strings so that we can treat them properly in the coming stages. So the first one I see is MS subclass. This is a class, right? It's categorical, and we can actually get more information from the data description here. We just drag that up. Each feature is given some sort of metadata we can see. So MS subclass identifies the type of dwelling involved in the sale. So each of these is a unique type. That means it's categorical. So let's take data 1, MS subclass. And let me just make a copy of it actually. I'm going to call data 2 is the new copy of data 1, and we'll just modify data 2 here. So this column is currently an integer column, and I want to set it to a string column, like that. Alright, I want to look for any others. This is numeric, like the frontage, the area, quality, condition. These are all numeric. Year is also numeric. So I'm just looking through for any more categorical features. This is square footage, I believe, SF. So again, numeric. This is number of baths. So we have count columns, year columns, and then like metric columns. And yeah, I don't see any others. And I was looking at this before. I think the only one that's been encoded, the only categorical that's been encoded as numeric is the MS subclass. So this should be enough, just setting that equal to string. And now we can move on to missing value imputation. So first thing is to deal with the categorical missing values. So we do this first because we can't impute. The only way we can impute for categoricals is with the mode. So we sort of have to manually go in and do this. We can't use like numeric tricks to find the imputation. So for this, we're going to definitely have to look at the data description again, and this might take a while. We have to go through each feature now and figure out when should we fill with the mode, and whether or not a particular feature Like for example, this one. A missing value for this feature actually means something. No alley access. So here, the missing value is actually a valid value. It's not actually missing. Because it's specified that when we have a missing value, that actually has a meaning. So if for these types of features, we're not going to fill the missing values with the mode. We're rather going to set the missing value to its own value. And so there's sort of two different things we have to do here. We have to impute using the column mode, and impute using a constant value. I'll use this one first, actually. So what I'm going to do is for each of these, I'm going to create a for loop for a column in, and I'll specify the columns here. Maybe I'll put them in a list like that. For each one, we're going to take, what is it, data 2 we're working with? We're going to call fill_NA on the column using a different method. So for the constant value, I think it would be okay to use the same value for all of these, which we can say none. So we're going to fill none in the case where a missing value actually means something. So let's find another one of those where NA is given a meaning. Yeah, here. So NA means no basement. So we'll just encode no basement as none. And that way, the NA is no longer missing, but is actually given some meaning. However, other ones, like this one, this does not have a specification for NA. So if we had a missing value in this column, we would fill with the mode, because that's actually a missing value. Does that make sense? If there's any questions, feel free to ask them in the chat. So for this one, we'll fill with data2 subcolumn dot mode. And we're going to subscript with 0 here because the mode can return multiple values. Okay, now we're going to populate these two lists here. We're going to populate them as we go through all the columns. So let's look at data2.isNA dot sum. And actually what I'll just do is ask if a given column has at least one missing value. So this is true, false, and then we'll use that as the as the indexer for data2. We have a problem. Okay, so let's just do .loc, target all rows but just the columns that match this condition. And then we can type .columns to get just the list of those columns. So let's go through each of these columns now, and sort of, because these are all the columns that have at least one missing value. Oh, you know what I realized? We should only be doing this for object columns. So let's do this. Data2.select dtypes object. Alright, here are all the object columns with missing values. So we're going to go through each one and check the data description to figure out what we should do with it. So MS zoning, we already looked at that. That's the first one here. Oh, actually, no, that's a different one. Okay, MS zoning does not have a special meaning for a missing value. So we're going to take MS zoning and put it into the mode imputed columns. Then we have alley. So let's search for alley over here. You can see NA is given a specific meaning. So we're going to put the alley column into the constant value imputed columns. Then we have utilities, and that does not have a value for NA, so we're going to put that again into the mode imputed columns. Then exterior first and exterior second. Exterior first does not have a value for a missing. Exterior second also no value for missing. So both of these are going to be mode imputed. So we'll put that up here and up here. Okay, so mass, I think it's masonry veneer type. Search down here. Here it is. Okay. Masonry veneer type. There is a none value, but that's not a missing value. There's no meaning for a missing value, so we do want to fill with the mode for this column. Okay. So put it up here. Okay, so basement quality. Here's basement quality. There is a meaning for basement quality. So if a missing value in the basement quality column actually means no basement. So we're going to encode this as none. This is the constant imputed value. We also have basement condition, which is right here. Also, NA means no basement. In fact, all of these basement columns, you can see, they all have no basement as the meaning for an NA. So let's go and let's go fill those in. So basement quality, we added. Basement condition also gets constant imputed. Basement exposure also. Basement fin type, just double check here, you can see the NA still means no basement, so we'll put that here. And basement fin type 2 also, no basement. Okay. So going down the list now, we have electrical. I know this is very tedious, but this is a very important part of the process. We don't want to fill with the wrong kind of value. And the electrical column has no meaning for NA. So we're going to fill with the mode here. After that, we have kitchen quality. And this has no meaning either, so we'll fill that with the mode. Then we have functional. This one has no meaning either, so that gets filled with the mode. We're almost done here. Fireplace quality. This does have a meaning for NA, which is no fireplace, so this will be constant imputed up here. Garage type, and there's a bunch of different garage columns here. Here's garage type, and you can see there is a meaning for NA, so this will be constant imputed. And we also have garage finish, garage quality, garage condition. Let's just look at that. So I think they all have this meaning for a missing value. Yeah, so we'll constant impute all of those. So garage type goes in here, as well as finish, quality, and condition. Alright, only 4 more features now. So pool QC. This is pool quality, and NA means no pool, so that is also constant imputed. Then we have fence, and NA means no fence, so that's also constant imputed. Then MISC feature. Let's look at that. Here it is. NA means none, so that also will be constant imputed. And there's only one more, which is sail type. And for sail type, there is no meaning for missing value, so sail type will be mode imputed. Alright, we finally finished with that. So we've binned them into their proper filling methods. And now we're going to try this out. So run this. We get an error. Oh, I forgot a comma probably. Yeah. Okay, so let me just rerun the notebook from the top. And yeah, okay, so now let's look at is NA. It should be data 2, right? Alright, and most of them have been taken care of. If we look at the is NA for the object columns, which is what we just worked with, and we sum across the columns as well, we have no missing values in the object in the categorical columns. Now if we look at the number columns, we do have some missing values. So that's what we'll deal with next. Let's just make a new copy, data 3, which will be data2.copy, and then work on the numeric missing values. Alright, so for numerics, we could do mean imputation, but I actually think there's a better way to do this. We can impute in a more intelligent way by using the rest of the data. And because we have the test data available to us, we can actually we can use Knn imputation. So k nearest neighbors imputation, which basically when you have missing value, it just looks at the examples around it to try to figure out what that value should be. So we're going to define our own. We're going to use the Knn regressor for this. Now I know there's a Knn imputer object from sklearn, but I actually want to use the regressor. So from sklearn.neighbors, we're going to import kneighbors regressor. I'll show you how we'll do this. So let's look at these values. So data3.isNA.sum. Let's actually just look at the numeric values. Select dtypes, numpy.number.isNA.sum. So there's actually not too many in here. And remember, this is the train and test set combined into one, which is data3. So let's look at what we want to do. The train and test set, for these purposes, we don't need to worry about the target, right? The target, we only have target examples for the train set, but that doesn't matter because we're not going to be using it for this imputation. So the train and test set both have useful information that we can use to impute the mean. Or not the mean, rather the Knn value. So we're going to create a kneighbors regressor here. And this is going to work by looking at surrounding data points and then filling in based on that. So why don't we create a function, Knn impute. This will take in a data frame and a column, and it will return the same data frame with the column's missing values filled in. So we'll start off by creating a copy of the data frame so we don't modify in place. And when we're working with the data frame, we can only use the numeric data to calculate the nearest neighbors, right? So we're going to create this numeric df, which will be df.select dtypes, numpy.number. So this will be just the numeric columns, right? So if we return this here, and then call Knn impute on data 3 we're on? Data 3, and let's say we're doing the garage years built column. Not going to matter at this point because we haven't specified any functionality for that. This will just return, currently it's just returning all the numeric columns of data 3. So these are the only columns that we can actually use for the Knn imputation, right? So how are we going to do this? We have to consider there are columns in here with missing values. We don't want to use those missing value columns when we're doing the Knn imputation. So we're going to create this non-numeric columns. Sorry, actually not numeric. Non-NA columns. So these are the columns that have no missing values. And we'll get that by taking the data frame, typing isNA.sum, and this will return like the sums of missing values for each column. And we'll ask, is each one greater than 0, meaning do we have at least one missing value? Actually, what would be better is if we ask if it's equal to 0, which means there are no missing values. And then so up here you can see if we ask is this equal to 0, then we get a true false wherever we have no missing values. And we can then use that as the indexer for data 3. Sorry, I have to do it this way again. Oh, right. Okay, that's because let's not look at the numpy number columns. Okay, what this would do is it would just give us the columns that contain no missing values. So that's what we want here. We should be doing this with numeric df though. So we'll use that as the indexer here. And then we'll type .columns just to get the column names. So non-NA columns are just the columns with no missing values. So we have the number data, numeric data, and then just the columns without missing values. So now we want to target this column that we've passed in. Maybe we can call it NA target, which would be better. This is the target with missing values that we want to. This is the target, the column that we want to fill. So what we're going to do is use all the rest of the data to as the neighbors for this data. So okay, we're going to sort of create this temporary train test set here. Y-train is going to be all the values of target that are not missing, right? So all the values of a column that are not missing, we're going to use as our Y-train. Which so to get that, we will take the numeric df, because we're only going to really be working with numeric df, and we're going to target NA target, but we only want the values that are not missing, right? So .loc, we'll okay, let me think. Maybe it'd be better not to do this yet. What are some pre-trained models which I can try in this project? For this particular project, you wouldn't really use pre-trained models. If you're doing some sort of deep learning with image classification, then pre-trained models can be really useful. But for this case, we're not even on the model selection aspect yet, so let's wait before we talk about that. Okay, so what we want to do is get all of the values in our NA target that are not missing. So first, let's actually do it out here because it's a bit confusing. We have data 3. Let's use which one should we use? Well, we have to find one with missing values in it. Alright, how about lot frontage? So this is up here. Lot frontage will be our NA target. This is the column that we want to fill missing values for. So let's look at it. And then I only want the rows that have missing values. So we can type .isNA to get the true false for just this column. And then we can do data3.loc using this as the row indexer and lot frontage as the column indexer. And that will give us all of the rows that have missing values. So actually what we could do is equals true to get the missing values and equals false to get the non-missing values. And that will give us, if we, right, so this would be our Y-train right here. So let's just put this in here. Except instead of data 3, we're using numeric df. And so these will be all of the lot, instead of lot frontage, we're using NA target. So these will be all of the examples of the data points in our NA target that are not missing. That's going to be our Y-train. So that's going to be like the labels or target data for the regressor that we're going to train. Then we'll create our X-train. This is going to be the rest of the data that the model is going to be using to try to predict the value to impute. And here the X-train is going to be all of the other columns for the same Y-train examples. So ytrain.index will give us the indices that we need. And we can use ytrain.index as the indexer for the rest of the data. I'm wondering if it would be better to just use this, what we did up here. I think it would be less confusing if we did that. Let's take that. We still want these values, right? These are the all the values where there are no missing value in the target column. So we can just copy this over, I guess. The only difference here is instead of the column being NA target, it's going to be all the rest of the columns. So in this case, that would come from non-NA columns. I think we should actually drop the NA target here, because we don't want to also include the NA target in our non-NA columns. Actually, it wouldn't be included because there would be a missing value there. Okay, so here our columns are the non-NA columns. Here our column is the NA target, and then our X test is just going to be the very same thing, except these are all the examples where we do have a missing value. I know this is a bit confusing, but let's see how it works. So this is X test. Okay, I just want to double check this, make sure everything's working. I think this should be good. So Y train are all the values of NA target that do not have missing values. X train is all the values of the rest of the data that do not have missing values for the NA target. And the X test is all of the rest of the data that do have missing values in the NA target. Okay. Now we'll create the regressor. Let's call it Knn. That's going to be a k neighbors regressor. And we'll call knn.fit on X train Y train. And then our the values we're going to impute are going to come from the predictions. So our Y pred will be knn.predict on X test, and these are the values we're using as the imputation. So we're going to take our original data frame called df, and we're going to index at essentially this, right? So let's look at this. This right now is the Y train. This is what Y train looks like. If we change this to true, that means this is all the values in NA target that have missing values. Now I changed numeric df just to df. This will modify the actual data frame. And if we set these values equal to Y pred, we're essentially filling in all the missing values in the NA target using the predictions we came up with. And at the end, we'll return df. Okay, I hope this is not too confusing. Let's try this out now. If we run this using just the garage year built column, we should no longer have any. Actually, let's use lot frontage. So if we look at data 3, dot is NA, dot sum, you can see we have 486 values, missing values in lot frontage. Down here, if we check the isNA.sum, you can see the values for lot frontage have been filled in, and essentially they've been filled in using the surrounding data in the feature space. Alright, so now we want to do this for all the numeric values. So just clean up the notebook a little. So let's look at what our remaining missing value columns. Oh, sorry, not X, data 3. And let's look at all the ones that have at least one missing value and use this as the indexer for data3.columns. So here are all of our numeric variables with missing values. So for column in this list, yeah, let's just indent it a little nicely. Alright, so for each of these columns, we're going to take data 3, take the column, and set, actually no, just set all of data 3 equal to Knn Impute, which is our function, passing in data 3 and the column in this for loop. So this will just fill all of the missing values in each of the remaining numeric variables using this Knn imputation strategy. So we'll run that and look at data 3 now. The isNA matrix, and then sum over the rows. And we have no more missing values in the whole data frame. So here our total number of missing values is 0. And we're essentially done with the cleaning part of the process. The last thing I'll do is create data 4, which will just be a new fresh copy of data 3. So now we'll perform the next steps on data 4. Okay, let's look back at our list here. So we're done with cleaning. Next, feature engineering. Alright, so I might come back to feature engineering because it's quite... We should probably come back to it after we train our first model. We just want to get a baseline down. We'll definitely come back to feature engineering. So let's put that on hold. And now feature transformations. So I do want to do feature transformations. So the reason to do feature transformations. So certain models will perform better when the data it's taking in is normally distributed. And you can't always guarantee a normal distribution from a feature column. So one thing you can do is you can look at the skew of a column. And by skew, let me just, if you're not sure what skew means, it basically means that the data sort of leans to one side. So here you can see skewed data looks like this. You can see the mean is off to the side to one point. So you call it a positive skew when the mean is to the right of the mode, and a negative skew when the mean is to the left of the mode. And there are various tests you can use for skew, but essentially what we can do is we can help correct the skew of a variable by applying a transformation to the variable. So for the test we're going to use, we're going to get it from scipy.stats. So I'm importing that at the top. And scipy.stats.skew will return the skew for a given column. So let's look at this. Data3 .select dtypes, numpy.number. These are all the numeric features, and this skew thing only applies to numeric features. So let's pass one of these in. Let's look at lot frontage. If we pass this in here, it will give us a value for skew. And essentially, this value, 0 means there's no skew, it's perfectly normally distributed. A positive value means it's right skewed, and a negative value means it's left skewed. And in general, if you have a value of over 0.5, you can consider the data as skewed and maybe in need of a transformation. But that 0.5 threshold is just a standard. You can experiment with that to your liking. So what we'll do is let's just look at each of these numeric columns and figure out which of them need to be corrected for skew. So what I'll do is sort of create this like little data frame so we can visualize this. I'll call it maybe skew df. And let's take, what is it, data 4 now? Should be looking at data 4. Let's take data 4. And we're going to, so we'll start off by just looking at the numeric data. Data4.select dtypes, numpy.number. I'll hold off on that. And what I want to do is calculate the skew for each of these. So we could call scipy.stats.skew on this data frame, and that will return skew for each column. So this is one skew for each column, for each of the numeric values. And what we can do is turn this into a data frame. Trying to think of if there's a better way to do this. Okay, yeah, we'll actually add the column. So let's start it off like this. Let's take, let's not do skew yet. Let's take the column names of the numeric features and use them here. And then give this a column name of feature. Alright, so now we're going to add to this, and we're going to calculate the skew for each of the columns. So we'll call this skew df. And now let's add a new column of skew df called skew. That will be the skew of the given column. So what we can do now is just take the feature column, skew df subfeature, and apply a lambda function here that for each feature we calculate scipy.stats.skew of the feature. Rather of data for subfeature. And now you can see the skew value associated with each column. And using this, we can now figure out which of these we want to transform. So one thing I do want to note is that we have some negative values. And it doesn't matter which direction the data is skewed in. We want to just sort of look at the absolute value of the skew. So we're going to take skew df make a new value called absolute skew, and all that's going to be is take the skew column and apply the absolute value function to it. And now you can see when we have a negative, that just becomes the positive version of it. Now what we can do is sort of threshold this column. Whenever the absolute skew is greater than 0.5, then we'll apply the transformation. So we'll create this last column called skewed. So this is if the column is skewed, and that will take the absolute skew column and apply a function that maps to true if x is greater than 0.5, maybe greater than or equal to 0.5, and otherwise maps to false. And now you can see anytime we have a skew value of over 0.5, then we have a true for that the column is skewed. And now what this allows us to do is query the data frame for all rows where skewed equals true, and then we type subfeature, and we get all of the columns that are skewed. And so we can now apply the transformation we need. So what's the transformation we're going to use? So we're going to use the log transform. Log transformation. Let's look at this. So this is sort of what it looks like. If you have skewed data beforehand, and you apply a logarithm to each value, you end up with it looking much more normally distributed. And so this can help the models deal with tiny values. So especially when you have something like this where all the values are concentrated really close to 0, sometimes this can be numerically unstable. And so by applying the log transform, it sort of spreads them out over a much nicer range. So all of these we're going to use log transform on. However, there is one issue, and that is if we look at, let's look at this dot values. So it just gives us an array of them. If we use this as an indexer for data 4, so this is just the skewed columns, the skewed portion of data 4. If we type .describe on this, you can see the minimum here has some values at 0. And as we know, the logarithm function is undefined at 0. Now, we don't have to worry about negative here because we don't have any negative values. All this is mainly real-world data, and there are no columns here that would correspond to that would have a negative value, a meaningful negative value. So because our minimum hits 0 at some point, we can't just do the log transform. Let's look at Desmos so we can see this. If we look at log of x, at 0 it's undefined, right? Log of 0 is undefined. So we have to compensate for this, and what a useful trick we can do is by adding 1 to x. Right. So now anything at 0 will go to 0, and the rest of the domain is evaluated. So we don't have to worry about negative values. So by shifting by 1, we actually we cover that case where we have a 0 there, because now a 0 is defined as 0, and anything above 0 gets just put on this scale here. So NumPy has a built-in function for this, which is numpy.log1p, which is log1 plus. So if we put 0, 0, 0, 1 like that, you can see it evaluates very close to 0, which is what we'd expect to see. A value really close to 0 evaluates really close to 0. Why don't I just name this house price regression competition. Okay. Alright, so whereas if we did this for log, if we just used log, this would be fine, but if we had 0 directly, we get negative infinity, divide by 0 error. Where if we do log1p, passing in 0 is fine, it just results in 0. So this is the function we're going to use to transform. So down here, we'll take, I guess you can say for column in this, right? We're going to query like this. And we don't have to actually do, no, we should actually. Okay, so for each of these columns, which are the skewed features, we're going to take the column, which is this data 4, yeah. Data 4 subcolumn equals numpy.log1p of data 4 subcolumn. So this is applying the log transform to each of these skewed columns, and that should give us the results we're looking for. Alright, so now if we were to run the skewdf again to check the skews, we may still have values. You can see most of them have been corrected. We still do have some skewed columns, but generally applying the log transform once is good enough. We don't have to worry about that. Okay, so now that we've done feature transformation, there actually is one more in here. So this month column, and this is interesting. We can actually apply a sort of a creative feature transformation here. Let's look at this column, month sold, and notice it wasn't skewed, so we didn't actually log transform it. It's still in its original form. So month sold, this is the month, right? So this is an integer column. It's still numeric. It still progresses. But the thing is, what is it really saying? What does the month mean? The model is going to look at this and think a value of 1 is less than a value of 12. But if you think about it, this is a cycle. It's a cyclical feature. So the 1 and the 12 are very closely linked. If you think of it in terms of temperature, time of year, if you're in the northern hemisphere, then a 1 or a 12 would be a really cold time of year, and a 6, or in the middle of the cycle, would be a really hot time of year. Right? So a low or high value of this variable means cold, and a medium value of this variable means hot. But that sort of complex relationship is not so easy for many models to figure out. And it would be easier if we applied a transformation to this that could compensate for that. So what we're going to do is actually use a sine transformation or a cosine transformation of the variable. So what we want is using this sine transformation that can set it so that a value of 1 and a value of 12 are very closely linked. So what we can do, this takes value from 1 to 12. We can sort of imagine a extra value of 0, where 0 would be equal to 12. And if we go into the graph and we look at the sine wave, you can see this can sort of replicate what we want. Right now, you can see that one period it stretches from 0 until 2 pi. But we can stretch this out with, if we add a little variable here, c, that can stretch the frequency of the sine wave. And what we can do is stretch this out so that the one period lines up at 12, which is right here, right? So if we keep stretching this until we get the period to line up at 12, let's make this a little more fine. Let's find a good value, the closest value looks like 0.5, so it'll range from 0.4 to 0.6, stepping by a small margin. And you can see we can now tune it so that it lines up right at 12 like that. And we want to get as close to 12 as we can within reason. So I think even if we step by one more, we're almost there. Looks like if 0.35 is really close, 0.36 is even better. Alright, so that's really close, right? That's really close to 12. So if we use this function now that we've created, what this function does is it takes a value between 0 and 12 and maps it onto this sine wave. So what would be, right now it's saying that a value of 0 and a value of 12 are very close. So a value of 6, however, is also really close, which is not what we want, because we want 6 to mean hot and 1 or 0 or 12 to mean cold. So what we actually would want here is a cosine wave instead. Cosine wave will map 0 and 12 equal to each other, but 6 will be on the polar the other end, right? It'll be, so here this means cold, hot, and these two mean cold. And maybe just for our sake, we'll make it a negative cosine, so that negative means cold, positive means hot. And so this is a really good function to use to sort of map the month feature into this sort of cyclical feature, where a low value of the feature means it's cold and a high value of the feature means it's hot. Whereas before, the model would sort of have to decipher that on its own. So using this sort of sinusoidal transformation, we could capture a lot more of the useful information in the feature. So here is essentially, let's just plug this in here. This is going to be our function that we're using, right? So let's bring this back into our notebook. And so this is the function we want to, let's just clean this up a little. This is the function we want to apply to every value in this month column. So let's take the column, and we can actually just apply it element-wise using numpy dot cosine of the column. So that's just the cosine transformation. Let's shift it by this value here, and then negative it. So here is the function that we're looking for. And if we now look at this, the min of this, actually we'll use numpy.min. The min should be very close to -1, right? Because we saw -1 is the minimum here, and it should exist on either side of the original data. And the max should be 1. And it is very close to 1. So the mean is, well, it's slightly higher. Actually, mean isn't telling us here. But what this does essentially, here, let's take this function, put it here. Instead of passing in the whole column, let's just pass in a single value. If we have a value of 1 for month, that means January, we get a negative value to mean it was cold in that month. If we have a high value, let's say December, which means the end of the year, we should also get a negative value, which means it's cold. But if we have a medium value of, let's say, 6 for June, we get a high positive value, which means it's warm. And so this feature now is able to recognize warm and cold, or summer and winter, whereas before it had to look at how the beginning of the month, beginning of the year and the end of the year were both cold, and the middle of the year was warm. All right, so yeah, so let's use this. So this is what the transformed feature looks like, and we're just going to set that equal to the new feature, like so. Yeah. Alright, so we can say this log transform for skewed features. And here we have the cosine transform for cyclical features. There is only one, though. Alright, so we'll run this, and now we look at data for sub-month sold just to confirm that it's been applied, and you can see they do take values between -1 and 1. Alright, and now last thing I'd like to do is create a new data set called data 5, which will take data 4 and make a copy of it. Alright, so we're done with feature transformations. Now we have encoding. Now encoding is pretty easy for us because we early on we set the proper data types. We made sure that all of the categoricals are encoded as strings. That allows us to just encode categoricals. That allows us to just take data 5 and we can actually just call pandas.getDummies on the whole data set. And that will do is create the one-hot columns for all of the categorical or string columns while leaving the numeric columns intact. So this just sort of takes care of the whole encoding for us. And we're doing this still on the train and test set combined, which allows us not to have to worry about columns being in one set and not in the other. And because this test set was provided to us or the competition, it's good to just it's giving us that extra bit of information we can use to preprocess. So I think this is fine. I think we can just say data 5 equals this, and that will take care of the whole encoding for us. And yeah, there were no more ordinal features, right? Everything was encoded properly, so all of the categoricals just got their own columns, and this should just completely take care of the encoding for us. So data 6 now is just a copy of data 5. That's the encoded version of it. Alright, and now I guess we'll do scaling. So let's go and import a standard scaler. I think standard scaler tends to be better. So from sklearn.preprocessing, import standard scaler. Because it does center the data as 0, which I like. A lot of models, it seems like, prefer that to just let's say min-max scaling, but I really think it depends on the data set. So we might consider changing that out and seeing which is better. We'll start with a standard scaler, which will just give each column the same range of values. So we'll fit this on all of data 6. And then just transform data 6 accordingly using scalar.transform. So right, I was going to say we're also using the train and test set for the scaling. So we're giving the scaler more information to look at by including the test set. Now, because this is not a natural production model, this is a competition model. We're able to just do this encoding like this, not worry about the input to our model. We're not using like an input pipeline here. Same with the scaling. We can just completely transform it to scaled data. We don't have to consider like inputting human readable inputs into the model. But if you were doing a production model, which I will cover in like a future video, you want to approach this encoding and scaling process in a very different way. Okay, but we're transforming using the standard scaler, and that does return a NumPy array, so I'm going to turn it back into a data frame after. I'm going to keep the indices the same as they were before, and the columns the same as they were before. And we'll look at data 6 now. It should be a scaled. Yeah, so all the columns are now centered at 0 with a variance of 1. And we can ensure that there's no like single valued columns here because we didn't fit it to one train set and then transform the test set. Okay, so now that we've done scaling, I think we could just cross both of these off. Target transformation. So this is interesting. Let's look at this. Target transformation is going to be done separately from the feature transformation because when you're doing a target transformation, you have to be very careful when you're evaluating the model. Because when you transform the target, essentially you're changing the unit in which the model is making predictions. So if you want to sort of analyze the model's predictions, you have to make sure you undo the transformation after the predictions have been made. So let's look at the distribution for our target. So we save the target in target, and this is just values for the train set. But we can plot it, or we can get a histogram to just see how it's looking, and it is looking sort of skewed, right? So this might benefit from a log transform. So I think we can do better than this. Let's actually import matplotlib, pyplot as plt, and seaborn as SNS. And down here now, let's create a, the dist plot from seaborn has been deprecated, but it's a really useful function. I'm still going to use it. So we'll set a new figure. I think I'll actually do 2 subplots, so we'll make a 20 by 10 figure. And then we're going to use sns.distplot, which is, like I said, a deprecated function, but it allows for this amazing parameter called fit, which I'll show you in a second. So we're going to plot the target and show this. So right now, just saying it's deprecated. This is what the target looks like. And you can see by default KDE equals true, which is the kernel density estimation, which gives us this line which sort of estimates the density of the histogram. And you can see that it is skewed, it's right skewed. So you can see that there's more data on the right side than on the left. So we can do a log transformation, and I just want to show sort of with this graph what that looks like. Let me include this. Makes it looks nicer if we do seaborn.setStyle dark grid. Yeah, it looks nicer. Okay, so let's make 2 subplots. Plot.subplot in a 1x2 grid. And this is the first one, and we'll do the second one down here. So we can also include this fit parameter. That's the second one, and we can we can pass in a random variable, and it can try to fit the random variable to the histogram, which is really, really nice. This is the part that was deprecated, like it hasn't been replaced by the new histplot function. Does not have this feature, so and so I'm still using this. So we can use it. We can get a random variable from the from SciPy, SciPy.stats. .norm, and we're doing normal because, again, the point of a log transform is to normalize or make the data look like it came from a normal distribution. So we're passing the normal random variable here, and you can see the black line is the normal, is what it looks like when we try to fit a normal distribution to the data, and you can see it's not lining up very well. It's not lining up with the data very well. So what we'll do down here, this will be without the log transform. And then we'll do it once now with the log transform. And that will be the same thing, except instead of passing in target, we're going to pass in numpy.log of target. And before we pass in numpy.log, we just want to make sure again that there's no that the minimum of this is higher than 0. Alright, so the minimum is above 0, so we don't have to worry about that being undefined at 0 thing happening. If there was a minimum of 0, we'd want to use that log1p trick again, but we're not going to do that. Alright, so let's look at what it looks like once without the log transformation and one with the log transform. And you can see that the normal fit is much, much closer to the data once we apply the log transform to the data. So you can see the scale of sale price has been changed. This is now log sale price. I should probably change that here. Plot.y label, or x label, is log sale price. So this is now a different unit, right? But it's much more normally distributed. So this models usually, not always, but usually prefer to see it like this. Okay, so we're going to actually apply the transformation now. So we're going to take the target and use numpy.log on it. But I'm going to call this log target, so I'm not going to overwrite. Run that, and now log target is normally distributed. Looks like this. Now we're going to make predictions on log target. So if we are to get back the RMSE, it would be in log sale price as the unit. And so what we'd have to do is afterwards, we'd have to exponentiate it, right? Do e to the power of log target to get back the unit in the original, I think it's dollars, the original sale price. So we have to just make sure after we make predictions on the log target that we exponentiate it again using numpy.exp, which is just the same as like e to the log target. Okay. So we did our target transformation. Now we can get on to actually working with models. So the data's in a good spot. We've cleaned it, processed it, encoded it, scaled it, did the feature transformations. One thing we didn't do is feature engineering, but I'm going to go back and do that after, as well as feature selection. However, I don't know how much feature selection will be useful here because we're not working with too many features. We have 317 columns. That's still a reasonable number of features. Feature selection is more useful when you have like a really high dimensional data and a lot of redundant information that you don't need. And it's actually negatively affecting the performance of the model. So I don't think we're really going to need feature selection too much. But let's look at this. Okay, so model selection. One tool I love to use for model selection is PyCaret. And so I think we have to install it here. So pip install, keep it quiet, PyCaret. And PyCaret is basically a low-code model selection library. It has a bunch of other features too. It can like automatically pre-process your data and stuff. But what I love about it is its model selection capabilities. If let's say like I don't want to import all the different models, load them in, do it manually, PyCaret just sort of takes care of that myself on its own. So from PyCaret .regression, the regression module is for regression tasks like this one. We're going to import two functions called setup and compare models. And as soon as this finishes, we'll just import this. And basically that will just generate a whole bunch of different models, run them on the train set or whatever set we pass in using cross-validation. So it automatically does the k-fold stuff for us using, I think by default, it's 10-fold CV, which is good. And then it gives us back metrics for each model to give us a sense, like a rough sense of which models are best for this data set. So we're going to run this to import those. And then down here, we're going to do the model selection. So we're going to call this setup function from PyCaret, and we should pass in the data we want to use. So I think it takes in data and target. So we have them stored as separate variables. Our data, we actually should split the data now, right? Because now that we're done with pre-processing, we should take the train and test set and make them separate again. So splitting, or split the data. So we never shuffled the data. So the test set is still at the bottom. What are we on, data 5? Data 6? The test set is still the last some number of columns here. So we can look back at the raw data now, which was called data 0. Actually, we had them stored as train 0 and test 0. And so the first 1460 rows belong to the train set. And the last 1459 rows belong to the test set. So if we just do .loc here, targeting, what we could do is train 0 .index .max to get the maximum valued index for this. What we can do is take all the rows from the beginning up until the max of the raw train indices and all columns. This will be the train set for the new data, for data 6. On the other hand, if we switch this, if we do from the max plus 1 until the end, that will be, oh, we got a problem. Oh, okay. Oh, alright. The issue here is that we didn't reset the indices on the test set. So we have duplicate indices in here. This one goes up to 1460 and then restarts at 0 and goes up to 1459. So let's go and reset the indices up here. When we make the split originally, after we combine them, we're going to type .reset index drop equals true. And then we'll just run everything below this. And that should... Alright, now we can see. So this is the test set, which is 1459, and that will line up with test 0. You can see the same number of rows. And this is the train set, which matches up with train 0. So there's 1460 rows, 1460, and then for the test set we have 1459 and 1459. So let's delete these and just look at, let's put these in their own block. So we'll call this train final. That'll be this thing, maybe .copy. And test final is going to be this thing, .copy. Alright, so well, actually, you know what? After it's been scaled, why don't I call that data 7, make that a copy of data 6. So we have working with a fresh copy. And we'll do this for data 7. Alright, and now train final and test final. Oh, you know what? Let me reset the index on this again. Because test final is going to have... yeah, the index doesn't start from 0. So reset index. Drop equals true. .copy. Yeah, okay, so here it is. Alright. Now we can do the model selection. So we're going to train on the train set and evaluate on the test set. We're going to pass in the data is going to be the train final. And the reason we have to only use the train set here is because we don't have target values associated with the test set. Alright, so the target here, now I think this expects that the target is attached to the train set, so let's actually just concatenate temporarily here the train final and the target. But actually we're going to use log target, right, because we did that log transform on the target variable. So we're adding these side by side. So axis 1. And then we're going to pass the target in as, what's a log target series name? It's called sale price. So target is sale price. Alright, so we can set up on this data, and now it's actually just looking through and making sure that all of the data types are the same. I'm sure it inferred it properly, so I'll just press enter on that. Oh, actually, let me just cancel this. I want to store this in a fake variable because it outputs a really big output. So enter. And this will just allow us to very quickly get a rough sense of which models are doing the best. Alright, so great to see you too, Satyam, thank you. Alright, so we have an issue. Okay, so I think that's just an error. Sometimes let me just try restarting the notebook and installing without the Q flag. I think for some reason I've gotten this error before. I just reinstall it. It seems to work. I guess we'll just run the whole notebook again. And while this is going, I'll actually be right back. I've used the bathroom. So as soon as this starts, I'll hit run all and be right back. Let's press enter on this to confirm. And it's finishing the setup. After this is done, all we have to do is run compare models, which again was imported from PyCaret. And now what this is going to do is go through a whole bunch of different models, fit it using tenfold cross-validation. Evaluate it using tenfold cross-validation, and it's going to rank them in order of score. So how well they're doing using the k-fold. And so it's looking like we have Bayesian ridge, Huber regression, ridge regression. Currently just like linear regression models are doing well. Unregularized linear regression is doing very badly, as you can see, as it usually does. So yeah, we're just gonna wait. This shouldn't take too long, but it's gonna, I think, eventually get into the more like ensemble type models. Looking like random forest is not doing so well. Gradient boosting not doing too badly. Orthogonal matching pursuit also interesting. Doing extreme gradient boosting now. Yeah, we'll just wait for this to finish. You guys have any questions? It should just be like another 30 seconds, probably 30 seconds to a minute. I don't know what we can do in the meantime. Yeah, this will be available after it's live, for sure. And I'll publish the notebook as well, so you can see the code. Okay, it's actually taking a little longer than I thought. I'm training some of these more complex models. There will be some amount of waiting going on here because when it comes to the model optimization, especially the hyperparameter optimization, we're going to be running studies on different hyperparameter combinations. So that can take a while. Could take quite a few minutes. I might sort of just cheat and use the studies that I found before, but we'll do at least one so you can see the process. Wow, this XG boost is taking a long time. I'm hoping that we get some better models in here, because right now the top 3 models are all very, very simple. Let's see, what can we do in the meantime? We could look at some graphs if you want. You guys know how log loss works? Pretty cool graph to look at, which is the same as binary cross entropy loss. In the case where you have let's call it yt for y true. This is completely off topic, but I figured we could use this to pass the time while this trains. Basically, we want a loss function. If you want a loss function for binary classification, this is the one that's most commonly used, which is called log loss, or binary cross entropy loss. Basically, this value can be either 0 or 1, which corresponds to the positive label, right? So we want a function that sort of accounts for both of these cases, when y equals 0 or when y equals 1. So what we can actually do is you take the natural log of x, where here x is the prediction. So at a prediction near 0, you get some y value. At a prediction near 1, you get some y value. And we're only concerned with this range here. So the function that's actually used is this yt plus 1 minus yt. times ln of 1 minus x, and then make this whole thing negative. And this is a really cool loss function because it switches back and forth. When you have y equals 0, then your loss decreases as your prediction gets closer to 0. And when you have y equals 1, your loss decreases as your prediction comes equal to 1. So this is very cool because the loss function changes based on the actual value for y. Let's see what we're on here. On cat boost, I think that's the last regressor. But yeah, for regression task, you would just use like mean squared error, which is, let's call it y. I saw your LinkedIn. You mentioned there are art students and how I started machine learning and became an expert. What do you mean art students? Or not? I was not an art student, if that's what you're saying. I was in computer science. My major was computer science, and I switched to applied math because I felt like it was drawing me more. And then going to applied math really helps with machine learning because there is a good deal of math behind it. Yeah, so that's almost done. Oh, it finished. Okay, let's look at this. I was going to just show you, basically a mean squared error just looks like a parabola. It's, no worries. This would be mean squared error, where the minimum means you have 0 error, and as you get further away, it goes up. And mean absolute error just looks like this, which means as you get close to the minimum, as your prediction equals the actual, you get 0. As you move away, you move up in a linear fashion as opposed to a parabolic fashion. Okay, let's get back to this. All right, so for cat boost, cat boost is definitely beating all the others by actually quite a large margin. What we're going to do is basically take the top 5 or so models, and we're going to bag them together. So this is a really useful way to improve the score of your model. The reason it works is each of these models it looks at the problem in a different way, right? So cat boost is doing one thing, whereas Bayesian Ridge is doing something completely different. We have like 3 proper linear regression models, and then we have this big ensemble boosted tree model at the top. And so they're both like taking very different approaches at looking at the problem. So maybe for some examples, cat boost is doing really well, but maybe for other examples, Bayesian Ridge is doing better. So there's like maybe a particular type of example one model is succeeding at, whereas for another type, a different model is succeeding. So what we do is we make predictions with all these models, and then we average the results. And so what you end up with is predictions that are sort of a reflection of many different ways of looking at the problem. And you can actually get much better results that way. So what we're going to do is, because cat boost won, we're going to import cat boost at the top. And now I noticed this orthogonal matching pursuit model came in 5th place. I actually know very little about this model, orthogonal matching pursuit. Let me just look it up real quick. So it would take me some time to understand this. It does look like they have it as a linear model here. We could just fit it and see how that works. We also have LightGBM coming in. So yeah, I guess yeah, let's just take all these top 6. Maybe even these 1, 2, 3, 4, 5, 6, 7, 8, top 8 of them. And just like write these down sort of. Oh god. Let me just type them out. Cat boost is number 1. Bayesian Ridge is 2nd. Huber is 3rd. Ridge, just plain ridge regression, is 4th. Then this orthogonal matching pursuit is 5th. And then LightGBM for 6th, was it? Yeah. gradient boosting for 7th, and then XGBoost for 8th. Alright, we'll just keep that there. We don't really need to see this anymore. I don't want to run this again because it takes time. This is just to get sort of a rough sense of which models work. So now what I'm going to do is go and import all of these up at the top. Alright, so from catboost, import catboost regressor. From sklearn.linear model, import Bayesian ridge. Huber regressor. I misspelled that. Just plain ridge regression, right? And then also orthogonal matching pursuit, which I really don't know how it works. Then from from light GBM, import LGBM regressor. From from sklearn.ensemble, import gradient boosting regressor. And from XGBoost, import XGB regressor. So here are all of our models that we're going to work with. So I don't know how many of these we should actually use. We could definitely try out different things. But let's do one catboost prediction and see how we score on the leaderboards. So this will be our sort of baseline model. Baseline model is going to be a catboost regressor. I'm going to set verbose equals 0 there because it does output quite a bit. Yes, Bertel, I would agree PyCaret is extremely useful, especially when you just want a very quick view of what models work. It's also, like I said, a lot of different features to PyCaret, but I mainly use it for this feature. Right, so we're going to fit this model on the train final, which is our train set, and we're predicting on log target. Remember, we applied this log transform to the target. Sorry, this should be .fit. And so as soon as that finishes, we'll evaluate it. However, to evaluate the model here, we don't have a test set, and I don't want to just do one train test split because it's there's a lot of variance in the performance based on which test set you use. So we're going to use cross-validation for that. So up at the top, I'm going to import two more things over here from sklearn.model_selection. Import kfold and cross-val score. It's a really cool function that I'll show you how it works. Basically what we can do to evaluate, we can take our model, we can call let's call the cross-val score to see what it takes. So cross-val score should take in an estimator and a data. It should also take a y. So the estimator is going to be our baseline model. The x is going to be our train final, and the target is going to be our log target, or y. Then we'll also pass in a scoring method, which in this case, if we look, hold on, sklearn scorers, I want to look at this. So there's a bunch of scores we can use. We're going to use MSE. So if we want to use mean squared error, we use negative mean squared error. The reason for this is just because by default, the way it works is by always minimizing the error, but always maximizing the metric we use. But because mean squared error is a metric that you should be minimizing, it just applies a negative to it so that it can maximize it instead. So negative mean squared error is what we're looking for here. So our score is going to be negative mean squared error, and then we also specify cross-validation to use. So I'm going to create a new k-fold object up here, which will make it 10-fold cross-validation. So n splits equals 10. And then we pass in kf as our cross-validation object. And so what this does is it's basically going to apply cross-validation to the train final, so it'll make 10 different splits, using each split as a test set on each run, and then using the other 9 splits as the train set. And in this cross-val score will return the result from each run. So I should probably store this in results actually, and then run this. And so at the end, what results will contain is a list of all of the negative mean squared errors for each run of the cross-validation. So it's just taking a while because it has to make 10 different. It has to refit the model 10 different times, one for each fold. But at the end, what we can do is take results.mean and maybe even plot the mean. We can maybe even plot the results over like a histogram. Let's do that. I'll create a new pie-plot figure. So plt.figure. Oh, and you can see it finished. Let's look at that. Here's results. You can see, so for each of the 10 runs, we get a negative mean squared error. And we should actually just negative this so that we can see them as the proper mean squared errors. So for each run, we get a different mean squared error. And we want to evaluate this. So let's just let's plot it over a histogram so we can visualize this more nicely. So I'll make a new figure with figure size 16 by 10. And then, okay, we could do it this way. So for name and okay, so we're not going to do that. SNS.dist plot again. We'll do another dist plot, except what we're going to do is use the results as what we're plotting. So this is just a histogram currently. Trying to think. Okay, let's do it this way. KDE equals true. So, I mean, this is just showing us basically the mean squared error for each run, right? So let's change the bin width. No, that doesn't work. Oh, number of bins. Let's do 10 bins. Okay. Alright, this is a little weird. I don't know if this is... whatever. Anyway, what you can see is that we get varying results. So what I want to do is just use the mean, numpy.mean of negative results, to get the mean squared error. So this is the mean squared error across all folds of cross-validation. Alright, so we have to try to get this into a metric that means something to us. Because you have to remember, first of all, this is already in the squared unit of the original target variable. So what we can do is square root it to bring it down to the root mean squared error. So this is RMSE. However, this is also not in the unit of the original sell price column. And the reason for that is, if you look at our target, and we made predictions on log target. So this is the log transform of the original target. And this is coming up as a value predicted within the log target range. So what we want instead is to convert it back into the original target value. So we're going to exponentiate it. numpy.exp of that will bring it up into the original target. So this is actually insanely good. You can see we have an RMSE, a average error of 1.12 in a range of this big. So you can see the minimum here is 39,000, maximum is 755,000, with a median of 163,000. So quite a big range here, and we're getting an average error of about 1, which is really, really good. But we can definitely do better, I think. So I think we should just make a submission. Let's see how we're doing. So let's do the submission process. So we want to look, make submission. When we're making the submission, we should refer to the sample submission to see what format it should be in. And so it should look like this. We did save the test IDs in test IDs earlier. And we also want these predictions, which will come from model.predict on the test set, test final. Sorry, that's called baseline model. And here it is. Okay, so baseline model. So these predictions are made again in the log of the original unit. So we're going to go and exponentiate them to bring them back up into the proper unit that we want. And we're going to call this predictions. Okay. Now let's take test IDs and predictions and put them together. So pandas.concatenate test IDs and predictions along axis 1. And actually it needs to be a series, so let's turn this into a series. And we have to make sure the column name is right. So the name of this column should be sale price. And here it is. So this is now looking just like this, right? We have 1459 by 2, 1459 by 2, and we have a prediction made for each of the IDs. All right, so let's call this. Let's call this one final predictions. And this will be submission. We'll look at submission. And now to actually submit it to the competition, all we have to do is type submission.toCSV, passed in the file path we'd like, which will be, let's call it submission.csv. And then I'm going to include index equals false so that these indices don't become a new column, and header equals true so that these stay as a row at the top, which is how it should be. Alright, we'll run this, and now over here in our working directory we have something called submission.csv, which I'm going to download. And I'm going to store this, make a new folder here. Okay, call it a stream. And then in here, let's call this 000 submission, which will just be the baseline submission. Alright, we get the submission. Let's go back to the actual leaderboards and hit submit predictions and drag that submission in here, and this will just be our baseline model. So make submission and let's see what we get. So we get a score of 0.1254. So let's jump to the position on the leaderboard. And okay, so this is actually my submission from before, so don't look at that. If we're looking at 1254, we want to look at where that comes in. So I'm just loading that. And we're going to scroll down to where that shows up. So that's looking like right around here. Right around here. 1254. So we're around 1700. And I'd like to get higher up. Hopefully I'd like to get within the top 1000. So how we can improve this? A big way we can improve it is by using ensembling. And so right now we're only working with one model. It's a cat boost model. It did show to be the best model of all of them. But if we use the other top models to sort of influence the predictions, we can get better results. So let's do that. So instead of the baseline model, I'm just gonna, I guess we could save this baseline. I don't want to do that. We'll just, actually I can do it as a quick version. Let's do that. Okay, now what we'll do here is do our bagging ensemble. So bagging just refers to sort of taking a bunch of models and averaging them up into like in parallel, training them in parallel, and then combining the predictions. So what we're going to do is create a bunch of models. So I'll make a dictionary as I usually do. That will map the model name to the actual model we want. And in this case, did I save it up here? No. Okay. Well, we still have the values from here. So we have cat boost, Bayesian ridge, Huber regression, ridge regression, this orthogonal matching pursuit, IGBM, gradient boosting, and extreme gradient boosting. So I think what we'll do is pick 5 of them. And I think what I want to do, I think I'm going to leave this one out. I don't know. Actually, we might want to keep it. We'll try them both. But I think, yeah, so let's just do the top 5 to start. We'll do these. So in here, yeah, let me copy this over. Just these ones. So we have cat boost, and that's going to be a cat boost regressor. Set for both equals 0 there. We have Bayesian ridge, which I'll call BR. That'll be our Bayesian ridge model. Huber, which is Huber regression. Ridge, which is just ridge regression. And OMP, which is this orthogonal matching pursuit. Alright, so we have our dictionary of models, and then we can train them for name and model in models dot items. We'll train the model first, model.fit on train final. And we're passing in the log target as our target. And we'll print out the name of the model followed by a message saying it was trained. Okay. So once they're all trained, we could go and evaluate each one to see how they compare. So I guess let's see this. What I'm going to do is create an empty dictionary here called results that will correspond to the results for each of the models. It'll start off as empty, and then for each name and model in models.items. We're going to calculate the cross-validation score using the model we pass in instead of the baseline model. And then we're going to set the element of results with the key is the name. We're going to set it to, let's call this result. And then we're going to pass this result into the dictionary indexed by the name. Okay, I think this is good. Let's run this. It might take just a moment because it has to go through all the models and train 10 folds for each of them. But hopefully we'll get, actually, you know what? Let me cancel that. Make it negative. Yeah, because I do want this in terms of the proper value. So we're going to square root it after we've flipped the negative sign. And then we're going to exponentiate it to get it in terms of the original target variable. Alright, we'll run that. And then I'd like to look at sort of their distributions in parallel. So we had this thing. I'll update this now to make it nicer. What I'm going to do is iterate through all the models for name and model in models.items. For each one, I'm gonna plot this distribution. And at the end, we'll call plot.show. Let's give it a title, which will be the CV error distributions. So seeing the distribution is more useful than just taking the mean across all cross-validation folds, because you can see if there's a high variance in the for a given model. All right, so in here, so instead of results, we're gonna take this dictionary, which it looks like it finished. Results now contains each model and the array of cross-validation RMSEs in the original target variable, in the unit of the original target variable. So we're going to take this dictionary, and we're going to take the name as the indexer for it. and we're going to plot what the value associated with that name in our results, which is that list of values. And let's see how this looks. Oh, it's plotting them all in separate ones. Why is that happening? What if we could try giving them labels? We can give it a label as being the name. Wow, weird. I'm actually not sure why it's doing this. I'd like to see them together. Let me try this. I have the code from before that I wrote. Oh, this is all messed up. Okay, hold on. I mean, we can look at each. Actually, all right, forget this then. Let's just forget this. I'll forget the visualization. We can actually just look at them with summary statistics instead. So results. What I want to do is for each for name and model in results dot items. We're going to print out the mean of the. We'll print out the name, maybe followed by some hyphens. And then we'll print out the mean of the results. Actually, call it result instead of model. So numpy.mean of result, and we'll print out the standard deviation as well. All right. All right, let me just do this at the beginning. Alright, here we go. So for cat boost, we have a mean of 1.12 and a variance of a standard deviation of 0.02. So you notice that the Huber regression has a very high variance compared to the others. And it looks like Huber actually is not doing so well here. It has quite a high mean as well. The other ones, though, are doing quite well, especially cat boost with the lowest mean. And this is the mean error across all folds. Alright, so let's see. Because Huber is doing so badly, I might consider using a different model in its place. So the next one on our list of models was LightGBM. So I'm going to go in and see if that works better. So we're going to try replacing this with LGBM. And that's going to be our LGBM regressor. And I'll call it LightGBM. And we're going to try refitting these. And then recalculating the results. So this is more of a slow process. I know this will take some time because we gotta be thorough with this. But let me show you how we're going to do the ensembling. So in here, combine predictions. What we're going to do is take each of these models. So in the models dictionary, which is going to contain the name and then the fitted model after it's been fit. We're going to take models sub, we have cat boost on top, so that will refer to the actual cat boost model, and we can call predict on test final. So this is the predictions for the test set using the cat boost model. And then again, like we did before, we have to exponentiate the predictions so that we get it back into the original unit. And then what we're going to do is weight it. So right now, we'll just multiply by 1.0, but we're going to add it. So let's call this final predictions. And include this in here. And we're going to add this to the same thing, but with the next model, which is Bayesian Ridge. And let's say we weight these by 0.5. That means half of the predictions are coming from cat boost and half of the predictions are coming from Bayesian Ridge. But what we'll do is add a whole bunch of other models as well. we'll do 5 and set these all to 0.2. So we have Bayesian Ridge, we have Huber, which we're going to replace with LGBM actually, like GBM. We then have our regular ridge regression, and lastly our OMP. So what this is doing is now it's combining the predictions from all 5 different models, weighting them by 20% for each, and then combining them together to create the final prediction. And these predictions are influenced by a lot of different ways of looking at the problem, whereas before with just a single CapBoost model, we were sort of restricted to one way of looking at the problem. Alright, so our results are in. Let's look at this again. Okay, so it's looking like GBM actually is doing much better than our Huber was doing. So a much lower variance and a much lower mean. So I'm sort of satisfied with these 5. So let's do this. We're going to make the final predictions. And you can see it's looking pretty good compared to what we had before. It's fairly similar. So let's see if this is better. Okay, let's do this. We're going to recreate the submission, this time using a different final predictions. Oh, and we do not need to exponentiate it here like this. We already created it. Okay, so this is the new submission. Let's now run this, download the new submission file, which we're going to call 001 submission, and see how this one does. So submit predictions, and we're going to drag this in, 001, and this is going to be ensemble, or bagging ensemble model, with 5 models. And let's see if this does better. Alright, so before we got a 1254, or 1245 score, and now we're down to 1236. So why don't I write this in our notebook? We should be keeping track of this. Our first submission got a 0.1245, was it? Or 54, I think. Now our second submission is getting a 1236, which is better. And now if we look at our position in the leaderboard for that, again, I'm just going to scroll past where we were. 12361. So we're not quite in the top 1,000 yet. We're around here, which is like 1,300 something. It's better than before, but we can do better, I think. And let's look at our checklist here. So we did our model selection, we did our ensembling, we didn't do feature selection. I don't think we will for today's model because we don't have that many features. However, we can still do feature engineering and hyperparameter optimization. So let's do feature engineering. Let's scroll back up. Let's go all the way back over here to when we were doing our preprocessing. And I guess right before we apply transformations. So after we fill missing values and before we apply transformations, we're going to do feature engineering. So let's see, can we create new features using some of the existing features? So at this point we're working with data 4. Thank you, Sadyam, that's very nice. But okay, so when it comes to feature engineering, it might be a good idea to look at what other people have done to figure out what features to use. Because there's so many different combinations of features we can do. So I might actually look at some other notebooks here. Maybe I should go to the leaderboard and then look at some of the top notebooks. To try to see, well, we don't want one of these because these are where the cheaters are lying, right? Because they've used external data in the model, which we're not doing. So we're going to go down to when we have some actual models. Trying to see, because there was one in here I found that was pretty good. Let me just see if it's still here. This one was good. Now this is actually also using external data, but he did have some very interesting feature engineering going on. So this is from Marto. Let's look down to when he does his feature engineering. Here it is, feature engineering. So he creates these new features based on previous features, and I am just going to copy his stuff here. I'll probably retype it over here. So this is what he had. So basically what he's doing is he's calculating the square footage per room. So what he does is he takes the total the living area, the area of the whole, which I'm not sure what this one means. Let's look at the data description again. GR_live above grade ground living area. So this is the whole living area in square feet, and he's dividing it by the number of rooms. So he's calculating the total number of rooms and dividing it dividing the total area by this. So that's a very useful feature that is more complex in its relationship. The model is probably not going to be able to piece that together. He also is taking the overall home quality by taking the quality and condition variables and adding them together. Getting the total bathrooms by taking the full baths, multiplying 0.5 by the half baths so that they're counted 1/2 as much. Adding that to the basement full baths and adding that to 0.5 times the basement half baths. So this is the total bathrooms, which is an interesting idea too. And then high quality square footage takes the square footage from the first floor and the square footage from the second floor and adds them together. So let's do this for ours. I guess what we can do is just change train test to data 4. And we could definitely go more in depth. I actually came up with a whole bunch of different features, but these looked like they didn't seem to improve the model by very much. These ones seem to have a good effect on it. So data 4, like that, and let's see if this works. Okay, that worked. Now data 4 has more columns than before. And I think we'll just leave it at that. I'm not going to do any crazy. This could take a very long time. This could take you as long as you want. You could find all sorts of creative feature combinations that you can use to create new features. So we'll create a new one, data 5 equals data4.copy. We'll run that, and then we have to just go through. We have to change all these. So this is data 5 now. Data 5. Scrolling down, this becomes data 5, data 5, oh, we don't need this. Oh, we do, yeah, data 5. This is data 6 now, and this is data 5. Over here, data 6, and data 7, data 6. Over here, data 7, data 7, data 7, data 7, data 7. Data 8. Alright, let's now run all the way everything before this. And that should go all the way through to data 8. Alright, now this still stays the same, right? The log transform is not affected by the data. But these should be data 8. And I think that's it. Okay, so now we have 321 columns, whereas before we had 317. That's due to these new numeric features that we created. Alright, so now let's see if we get an increase in performance using that. So we're going to recreate the models, refit the models, and I'm skip the valuation. I'm just going to go down to combining the predictions, getting the final predictions, making the submission, and then submitting. So let's look at this, downloading this. I'm going to call this 002 submission, and we're going to put it, you can see he used multiple data sources. He used another housing data set for this competition. Alright, let's make some predictions. We're allowed 10 submissions in a day. Passing that in, this will be the ensemble with feature engineering. And our score, let's compare it to before. Our score did go down, so it actually did improve our score. Alright, so what else can we do? So the hyperparameter optimization I'm going to do in just a second. First, I want to try one more thing. So by looking at this, it's clear to see that the CatBoost model is actually outperforming all the others by quite a bit. Now, the ridge is worse with a 1.46. The OMP is after that. Then is the Bayesian ridge. Then our light GBM, and then CatBoost is all the way at the top with a 1.12. And you can see there's quite a bit of jump from the light GBM to the CatBoost. So because CatBoost is outperforming all the others, what I'm going to do is actually weight CatBoost as being more important than the others. I'm going to give this a 0.4, and I'm going to take one away from each of the worst models. So that would be our ridge and OMP. So I'm going to lower I'm going to lower ridge to 0.1 and OMP to 0.1, and putting more emphasis on the CatBoost now. So I'll just run this. This is just a different set of weights and new prediction, and let's see what we get using this. Okay, so here's our new submission. Let's download this. This will be 003, and submit. This will be an ensemble model with custom weights. And we'll see what we get. 1.176. Let's compare that. And again, we are going down. That actually was quite a bit of improvement. So you can see that experimenting with custom weights is actually a good idea. And at this point, we're doing pretty well. We're probably nearing the top 1,000. Last thing I'd like to try before we call it a day is hyperparameter optimization. So there's a bunch of different ways to do hyperparameter optimization. You can just do there's, for example, the most basic one is a grid search. Mutual info regression, select percentile. Yeah, you can use mutual information when you're doing feature selection. It's a good way to know which features are most responsible for, or which are most related to the target variable. But the only thing is, our data set, if you look, we only have something like 300 features, 321 features. Most of the time, when you're dealing with such a small number of features, feature selection will inhibit your model rather than improve it, because a high number of features only really becomes a problem when your feature count passes 1,000, when it goes into the thousands, in my experience. Now, you can definitely try it out, there's no doubt, but when you have a high number of features, there's a bunch of problems. One, your models can be more likely to overfit. Two, it's much slower to train. Three, it's much more data to store. In general, when you have models when you have data sets with number of features in the thousands, or especially tens of thousands, that's when you want to sort of look for dimensionality reduction, whether it's by feature selection, or just some actual, like a PCA, principal component analysis dimensionality reduction, or something like that. We're not going to do feature selection this time. Okay, but I was going to import Optuna. So you can do grid search. For example, one way of hyperparameter optimization is grid search, where you just define a set of hyperparameter values to try out, and it will try every single combination of every single hyperparameter that you put in there. Only thing is, grid search is really expensive. It takes a long time to do, especially if you want to try out a bunch of different hyperparameters. Another way to do it is random search, which will just randomly pick hyperparameters from the grid. But the problem with random search is that it's not going to cover all of the hyperparameters. You may miss something here or there. So what I like to do is I really like Optuna. Optuna employs Bayesian hyperparameter optimization. So it's sort of doing it in like a smart way. It's using the information it's gathered to make decisions as to which hyperparameters to try next. And it's very easy to use. A great library. I definitely recommend it. So we're going to import Optuna. Let me close out some of these tabs, cluttering this up. Okay. So we're going to import Optuna here. Can we use recursive feature elimination here and then use grid search CV on the selected features? Grid search. What do you mean by grid search on the selected features? We can definitely use recursive feature elimination when we are dealing with too many features. It's also a great way to use feature selection, but like I said, we're not going to be doing feature selection just because of the I tried calculating feature importance using catboost's feature importance function. I had dropped like all of the low importance features, and there was very little change in the, I don't think any change in the model performance. So I don't feel like it's worth it in this context. Okay, but we are going to do hyperparameter optimization using Optuna. So I think let's do it before we actually create the model, right here. Let me delete this baseline model thing. We're not going to use that anymore. Hyperparameter optimization. So let's look at Optuna's docs. This is the format we use. It's a little small. Let me zoom in. Basically, it has this thing called a study. And a study basically looks at an objective function that you specify. So you create your objective function, and it just tries to optimize or minimize or maximize the objective function given a set number of trials. And at the end, it'll give you the best parameters, or the parameters that are most responsible for a good result in your objective function. So let's look at this. I'll just copy this over, and we'll sort of replicate this here. So we're going to create our own objective function. And actually, I want to create a separate one for each model. For now, we'll just keep it like that. And we're going to create our study, optuna.createStudy. And let's do this separately. Let's start with the objective function. So the objective function is basically a measure of how good a model's predictions are. This is the function we want to minimize. So let's do catboost first. So this takes in a trial. And so a trial it's an Optuna object that gets passed into the objective function automatically when you call this optimize function. And the trial is basically just it has some useful features like this, trial.suggestUniform. So what this does is basically it specifies a range of values from which to draw possible hyperparameters, and it uses probabilistic random variables, right? So suggestUniform is saying, well, we're suggesting that this variable x is coming from a uniform distribution with a support -10 to 10. So this will draw values randomly between -10 and 10 from a uniform distribution. So in here, we want to specify all of our hyperparameters. Let's do catboost. Actually, catboost is going to take a while, so why don't we do ridge? Let's do Bayesian ridge. So Bayesian ridge has some hyperparameters. An iter is number of iterations, a tolerance value. It has 4 sort of real hyperparameters, which are alpha 1, alpha 2, lambda 1, and lambda 2. You can read about what they do here. It has some initial values for those hyperparameters. And the rest is not really as important. So I think what we'll do is we'll try number of iterations, maybe tolerance also, and then these 4. So I'm going to use these. Okay, so these are the values we want. So we have n iter, tol, alpha 1, alpha 2, and lambda 1 and lambda 2. So in here I'm going to create those values. N iter, tolerance, right? Alpha 1, alpha 2, lambda 1, and lambda 2. And we're going to suggest a distribution from which to draw values for these hyperparameters. So we want to look at what they are. The default for n iterations is 300, and this has to be an integer, right? We can't use a float. So if we look at the documentations here, the documentation for Optuna, I think actually it would be on read the docs. Let me just get it. Optuna docs. Here it is. So I'm going to look at the API reference, and I'm looking at the trial object. Trial object has all these suggest functions. So we want suggest int, which will suggest an integer from a given range. So it takes in the name of the hyperparameter, the low value, and the high value. Alright, so in here, n iter is going to come from a trial.suggest int, and the default value is 300. So why don't we do something from 50 to 600? And we have to give this a name, n iter. But we'll try pulling value integers from between 50 and 600 for the n iterations. For tolerance, this is a float whose default value is 0.0001, I think. 1e to the negative 3. So for this one, we actually probably are going to want to use the log uniform, which is going to be a uniform distribution, but on a logarithmic scale. So it'll be more likely to pick values closer to 0 than it will large values. So suggest log uniform for that. Also name low high is the format. So trial.suggest log uniform. The name here is tolerance, and the default value is 1e negative 3. So why don't we make the low value 1e negative 6 or 7, and the high value can be maybe 10, although I doubt we're going to get up to 10. Okay, for alpha 1, this is actually way too high. Let's make it like 0.1. Okay, for alpha 1, now we also have very low values for this. So I think the last one, lambda 2, is also, yeah, they're all defaulted to 1e negative 6. So we'll use the same log uniform thing for that. This one will be alpha 1. This one is alpha 2, lambda 1, and lambda 2. Alright, and then let's change this to maybe 1e negative 8 for each of these. And maybe I'll bump this up to like 10, because I think these can take higher values. Alright, so we've defined where each of these hyperparameters are going to be drawn from. And now what we're going to do is train the model using these hyperparameters. So when the objective function is called during the study, these will all actually be realized. These values will take an actual value from this distribution. But for now, it's sort of ambiguous. It's just defining a probability distribution. Okay, so we're going to create a new model. And this is going to be the Bayesian ridge model. So be our objective. This is going to be a Bayesian ridge model. And we're going to pass in the hyperparameters. So niter equals niter, tall equals tall, alpha1 equals alpha1, alpha2 equals alpha2, same with lambda. So these are lambda, and these are lambda. Alright, so we've created the model, and now what we're going to do is fit the model to the train final and the log target. Then we're going to get the cross-val score. So this is all happening within our objective function. So CV score maybe is going to be cross-val score. Let's go back to when we evaluated over here. So we're taking the cross-validation score on, let's just copy this. Yeah, I'll copy this whole thing. Because this is what we're trying to minimize, right? So over here. Okay. So this is looking good. Just copy this out. Put it here. So this is the score we're getting. And I do want to take the mean of it. Now, I don't think I want to take the square root here. Actually, yeah, I will take the square root. I'll just take this whole thing. This whole thing I'll use as the CV score. And that's going to be using the model that we pass in here, right? So we fit the model, we create the model, we fit the model, we calculate the CV score, and that's the value we actually want to minimize. So this actually will return one value for each fold. So we're going to return numpy.mean of, let's call it CV scores. The mean CV score will be what we're trying to minimize. So this objective function takes, creates some hyperparameters, creates a model with them, fits them, calculates the scores, returns the average score, and then the study is going to run this function over and over again with different hyperparameters until it has a very low value that's returned. Alright, so let's do this. Where was it? Okay. So we're going to call study.optimize. So study is optune.createStudy, and then study.optimize. And for the optimize, we pass in the objective function and the number of trials. So the objective function is BR objective. That's the function we want to minimize. The end trials is, let's keep it at 100. And then we can also specify the direction, which is minimized. This lets you maximize or minimize depending on the direction. Actually, I think the direction goes up here. Okay. So now what it's doing is it's running the trial optimizing, and you can see it's doing trial 0, trial 1, trying out different hyperparameter combinations, and then we get back a value for each run. Actually, where is it? Here's the value. So this is the RMSE that for each combination of hyperparameters. So when it tries out all these different ones, it's going to basically keep trying to lower this value. At the end, we'll get back the best parameters, which will be the parameters that resulted in the lowest value here. Okay. So it's saying best is trial 16 so far. So we can look at trial 16 is here, which had the lowest RMSE value. So this will just take a second. I am going to go get some water, so I'll be right back. Alright, where are we? Trial 56, so we're about halfway done. It's going to take a little bit longer. What can we do in the meantime? I don't know, just sit and wait. Actually, in the meantime, I think I'm going to go back to my other notebook, because I'm definitely not going to do this for every single model. It's just going to take all day. So I did this before, like a few days ago. I'm going to go to my other notebook, which is this one, I think. And then I'm going to grab the hyperparameters that I found for the different models. I should have done it for the OMP model, because I didn't do the OMP model last time. Here are the parameters I found. So I'm going to copy these in over here. Actually, down here. So here are the parameters for each of the models. Huber we're not using in this case. And what we can do is just take these and pass them right in to the model definitions. We can unpack them like that with the double star. That will take each of the elements in the dictionary and sort of unpack them into this argument list. Alright, so BR, that's BR params. So we'll unpack the BR params there. LGBM, that's our LGBM params. Unpack, let me call it light. So what we have over here. Ridge params as well. So we'll just unpack the ridge params. And then the OMP, I actually have to look this up because I'm not familiar with this this regression model. So let's look at this. I'm actually not sure. Orthogonal matching pursuit. Okay, actually it doesn't look like it has really many hyperparameters. Okay, so maybe we don't have to worry about it. There's actually no hyperparameters here. There's a tolerance value, which I guess we could try both of these. So fit intercept. No, I'm not going to do fit intercept. Let's just do tolerance then. Let's see, is this finished? Alright, finished. Alright, so the trial is complete. The study is complete, rather. And after it's complete, we can just go here and say study.bestparams to get back the best parameters it found. And so this is what it found. Now, it's probably going to be slightly different from what we have over here, but we can almost guarantee it's a good combination of parameters. And this one was for the Bayesian ridge. So actually it trained for longer iterations. I didn't do tolerance last time. So, wow, it found a much higher value for lambda 1 than it did here. You know, I'm just going to use the ones we found. So I'll just replace that. And then indent these over. Okay, and then let's do the OMP study. This one will be much, much quicker. So let's copy this. This will be our OMP objective. Only difference is that we're not using any of these, just tolerance. And the default value for tolerance is none. Oh, this is weird. Okay, I'm not going to do this. I'm not going to do this. Just going to leave. So we just did one hyperparameter optimization. The rest I'm just taking from my other notebook. And for OMP, we're not going to even worry about it because there's hardly anything to optimize there. Alright, so running this, and then we're going to create the new models with all these new parameters. Fit each one of them. We don't need to evaluate. Let's just see how this does when we combine the predictions. Get our final predictions made now with optimized models, and make our submission to CSV. We can grab it over here. This one will be called 04. And let's see, go back to the competition here. Submit predictions. Drag that in. and this is ensemble with hyperparameter optimization. Alright, we'll make this a mission. And let's see what we get. 1.1208. So this is a huge improvement. This is the best score we've gotten so far. And you can see this is why it's a good idea to start with a baseline model and then just see it improve as you go. Because you can always tell if something doesn't work, you just fall back to the last step. So this is a good way to proceed. Alright, let's check. So let's check what this does, what this is on the leaderboard. 12108. And we are in the top 1,000. Now, I think this, it says it's not our best score, but I think it is. This is our best score. I think that's a glitch. So this is better than I've ever done. We're doing really well here. And we also should consider that a bunch of these are not really valid. Not so valid. Because they're using external data sources. So you can sort of see where that happens. You can see it's decreasing gradually. Still, and then suddenly it just jumps down really fast. And it's because these people up here are using an unfair advantage that these people are not. And I think that jump happens right from here to here. So from the first 275 examples, we sort of exclude. We're not even considering them in the competition. So from 276 until the end, which is 9,062. Let's calculate this. 9,062, and we're going to subtract 275. And then our submission. Can you do a video on tips and tricks on creating models on Jupyter Notebook? Well, the good thing about Kaggle is that it's pretty much, it's just built on top of Jupyter Notebook. So all of my videos are done in Kaggle. It's pretty much all the same. Are you talking about like keyboard shortcuts and workflow and how to improve, like actually this like just like the workflow of it? Because I could definitely do that. Sounds like a good idea. Okay, so I want to see sort of like how we're doing, excluding these cheaters on the top. So we came in 839. 839, but we also want to subtract 275. So we're checking how we did overall, and it looks like we're in the top 7%. So we're actually doing quite well if you exclude these guys on top. And you know, it's a competition. This is like a knowledge competition. There's no rewards or anything. Oh, they cheated because they used external data. You can see these guys on top. Here, look at this. Here's a notebook for one of the top submissions with a very, very low score. And if you look at what it's doing, it's actually just loading in the answers from some outside data sources. You see, so this notebook doesn't even contain a proper like pre-processing or anything like that. It's just loading in answers. All these guys, they're just loading answers for the to get a high score. And then down here, these are actually sort of valid. These people actually did. Let's see, try to find a good one. Like this guy, he has a much lower score than us. But if you look at what he's doing, he's loading in data from a different data source. So he's using more information than what we had available to us from the competition data source. You can see at the top he's using multiple data sources. It's because he's using the competition data, but then he's also using this extended data set, which contains more information than what was present in the original data set. So that's why I say it's cheating. I mean, it's just a like a knowledge competition. So there's no rewards or anything. So it's not really a big deal for cheating. But if we're sort of being fair with ourselves, we should only be comparing our results to people who were using the same data as what we got, as what we used. When do you decide to use pipeline and when do you decide not to? Right. So pipeline is use pipeline when you are creating a production model. So there's a big difference here between a competition model and a production model. A production model is a model that's going to be used by a customer or something in a real-time environment. All right, so a production model has to be very clean. It has to allow for human readable input. The user wants to be able to type in the name of the town where they live instead of having to like manually one-hot encode it themselves and then pass it in. For a competition notebook, you can see the inputs of our model, which looks like train final. There's 320 columns. Yeah, no problem. And you can see that it's already been one-hot encoded, already been scaled. So if someone wanted to input this model, they couldn't realistically enter the inputs because they're all so messed up already. They've all been transformed. They've all been messed with, scaled, encoded. But in a production setting, you can't do this. You need to have human readable, easy to input values. That's when pipeline comes in very useful because it allows you to pass in human readable values, and then all the pre-processing is done automatically after the input has been passed in. Whereas here we don't really care about this because this is just sort of just for the competition, right? Okay, so we're in the top 7%. I think that's a really good place to stop. Do you guys have any more questions? I can wait around for a bit if you guys have any more questions. Going on from here, I think. Yeah, no problem for the explanation. I think other things we could try would be. I think the best thing is for a competition. Once you have a working model, you should look around at other people's notebooks to try to see what they're doing, because there's, especially in something like the more advanced deep learning competitions, people are coming out with these crazy strats that are, you would never think of yourself. So it's a lot of what happens in those real competitions is that people are constantly learning from each other and implementing each other's strategies. And at the end, the person who usually wins is someone who sort of used everyone's techniques in a really nice ensemble manner. And yeah, it seems, in my experience, it seems that the real trick to competitions is ensembling. And really to model performance in general. By using so many different ways of looking at the problem and combining them in a meaningful way, you end up with much better predictions than just by using one model at all. Alright, so yeah, I guess that will sum up the live stream. Thank you guys so much for tuning in. I will probably be doing these every now and then. I'll also be coming out with some more videos with some more like in-depth content, exploring new libraries, I think I'll do one on production models as well. And if you have any recommendations for the channel, just leave them in the comments below. And thank you so much, guys, for watching. Yes, oh, wait, we have one more question? Okay. Oh, what's the best practice in segregating code into multiple files? Say pre-processing and model creation, should they be put in different files if they're really big? Yeah, that's a good question. So I don't have the most experience with big data. It is sort of a monster. I've heard YAML is good for storing a lot of data. I'm not sure though. I'll have to look into that, and maybe I'll make a video on that as well. Okay, but yeah, so I'll see you guys later. Thanks so much for watching. Peace.